Hello everyone, I'm Tejas. I currently work at AMD's CPU compiler team, and as a team, we are always trying to improve loop-based transformations, and vectorization is one of the important loop transformations for performance. So Ashutosh from my team will be representing loop-based loop splitting in upcoming session, and he also presented a improvement in loop vectorization with loops with control flow past year. So this is kind of an extension to that. So current state of loop vectorizer, LLVM loop vectorizer is very sophisticated that it can also vectorize loops with complex control flow. It can do if conversion, or it can also flatten the loop code using vector masks. And these instructions use these masks to vectorize the instructions inside this complex control flow. But there are always some missed opportunities or some patterns which are not handled yet. So one of those patterns is compressing store pattern. What is this compressing store pattern? First, we'll just take a brief look at how a control flow base, a complex control flow inside a loop is vectorized using masked instructions. So here in this example, we are loading scalars from A and B inside the if condition and storing the operation in C. So the mask is computed based on the condition at runtime. If it was compile time, it would have been hosted outside. So here the masks here is 0, 1, 0, 1. So for all the masks that is true, we are going to do the operation and then going to store at C. The important thing to note here is that the operation may or may not be contiguous. That contiguity is based on the condition. If it was all ones, it will be stored contiguously. If it was zeros, it won't be stored at all in this vector factor. So the compressing store pattern is nothing much different. The only case is that the store to C in this case is happening with a different variable, which is not the induction variable of the loop. The important thing is it is incremented at the same time where it is being stored, so it is contiguous. Even though the loads from A and B or the source or whatever, the operation is happening inside this predicated basic block may not be contiguous, but the stores to C are contiguous. So this is a pattern which is not supported yet. For this variable J, we call it predicated induction variable just because it is incremented in a predicated basic block. So how do we enable it in the LLVM vectorizer? Before going to that, let's check when it is legal to do that. So first case is pretty obvious. If J is being returned to apart from its increment in the conditional block, the value of J is being changed. That means the store to C may or may not be contiguous. So it's not exactly a compressing store pattern. So obviously we shouldn't be doing this. Next thing is pretty tricky. In the next case, J is being used outside the if condition. The issue here is that we know the value of J, what the value of J will be inside the predicated basic block where it is being used for the compressing store. But it is very difficult to predict or calculate the value outside of it because we don't know what the value will be if, let's say for the store to D, we don't know if it has taken the if condition or not. And it is, while vectorizing it, it is pretty difficult to predict or calculate that value. So we don't do the vectorization in this case. So when is it legal? It's legal. It's pretty restricted. So whenever J is being incremented inside this predicated block where the store is used, only then we can do this kind of vectorization. But there can be multiple stores using that variable, which is using that. So this is legal in that case. Also, all of these examples I have used post increment. It can also be a pre-increment, but in the IR level, the structure will be different, but it is still legal to do that. So what currently is happening, so I have an IR for the same example present there. I don't know if it's visible, but what currently happens is that if I use debug logs, first of all, it will bail out saying that it has found an unidentified file. So obviously for the loop for our predicated induction variable, the phi at the header, is not recognized. The reason is there are multiple reasons, but one of the reasons is that the scale is not as same as the induction variable, because we will not be able to calculate the scale as induction variable. For induction variable, the scale is something like start value, its direction, and the step. But that is not the same case for the predicated induction. But actually, it is, because so the increment for the predicated induction variable is happening inside the predicated basic block. But since we do not know if it is being incremented in each iteration, so the scale is not able to compute. So what we do, we compute the scale based on the assumption that the predicated basic block can be executed at each iteration. So it's basically similar to the induction variable. So we go ahead with that. Then the predicated induction, the compressing store, which is using the predicated induction variable, is marked as a compressing store so that we do not widen it. Then there is a phi which is receiving the predicated induction variable. We can get rid of this. So there are multiple ways to handle this, but it's just that we do not want to vectorize this. This is just a V plan, just to show that what we execute. Just one thing extra here is that we use pop count instruction because we don't know how many times the J is incremented, and pop count can count the number of zeros or ones inside the mask so that it will be updated accordingly. Just the costing part. In the costing part, we have an extra instruction which is pop count that will be added into the cost. Widening store, we use the compressed intrinsics cost. And there are no new recipes essentially, just one new recipe which is same for the induction variable. And the pop count is just a VP instruction. That's it.
Thank you.
Thank you.